Chapter 13, reaction rates and chemical equilibrium, rates and reactions. For the most part, we're going to go over and over this concept. We will do work sessions, so the lecture part of this, the recorded lecture part of this, will probably be shorter than the full. Well, it will be shorter than the full lecture for this. So we will pause and we will do some working through these problems. Okay? All right. So here we are, Chapter 13, rates, equilibrium. That's what we're going to talk about for the most part. For chemical reactions to take place, molecules have to come in contact with each other. Voila! If anybody misses that on my exam, I'm going to really stare at you really hard. Okay? It has to be contact. They have to collide. Per collision theory, a reaction takes place only when the molecules collide with the proper orientation and sufficient energy. It's like a docking of the space shuttle. Any other dockings that you can imagine. That's what happened. It has to make contact, has to properly collide, has to properly dock, which means it has to have the right orientation. If it doesn't have the right orientation or affinity for it, it's not going to happen. But collision is critical to that. The molecules have to collide or come in contact in some fashion. They have to get into each other's space. They have to get into each other's space with regards to their valence electrons. Okay? Valence electrons are what makes things happen. So it's invade that space. If the molecules are not aligned properly, no reaction will take place. So there has to be an alignment. But fortunately, you give these molecules enough energy, they will find the alignment. Okay? All right? So here's an example of nitrogen, which is a gas. It's a diatomic gas, which you know. And this is oxygen, which is a diatomic gas. They collide, and they find the right orientation, and they produce NO, and NO, which is, we call it a NOx. It's a pollutant in the atmosphere. Okay, so this is what happens. Reaction molecules must collide, have a minimal amount of energy, and have the proper orientation to form products. It must satisfy these rules. You get it? These set of conditions must be satisfied. Has to collide and have orientation. Okay, so watch for that. That question is on the exam. Three conditions must be met for the reaction to occur: collision, orientation, and energy. There you have it. This is, in this particular lecture, this is slide number 4. You will want to memorize this. This is a classical multiple choice question on my exams. The activation is the amount of energy needed to convert the colliding molecules into product. In this particular case, we start here with these reactants. And what happens, they push themselves uphill. And that's the energy needed to reach the top of the mountain to fall off the cliff, fall off the top of the mountain. So that's what's happening. You put the reaction together, it's a bit slow, and all of a sudden it takes off. It's like toast in the toaster. You put the toast in the toaster, and you push the little button down. Of course, I'm sure all of you stand there and you watch this toast, right? Of course you do. You stand and you stare at it, and you watch that moment when all of a sudden it just goes brown. That's the activation point at which combustion starts to burn the toast. I'm sure you guys have done that. You're kidding me.
I always accidentally wait until it's cold because I'm going in the
You got about your toast, right? But that's what's happening. You get it. It's activation energy. So there's an activation energy in these reactions, and they go up. Once they go down, they fall into product. Now, if the product is at a height above the reactant, that means the reactants are more stable than the products. If the products drop down here, the products are more stable than the reactants. In the case of nitrogen and oxygen gas, we know that nitrogen and oxygen gas are very, very stable, and these NOx are not. And this is, in fact, why they act as pollutants in the environment, because this particular, they have sufficient energy here to interact with other things in the environment, form these nasties that form brown-looking air. Get it? So, activation energy is this energy, this diagram. Okay? It's worth memorizing. I think we've had one look like this before. Reaction rates. The rate or speed, and many of us hate using that term, but the rate of a reaction is determined by measurement. That's what you know, that's speed. The amount of reactant used up in a certain period of time, the amount of product formed in a certain period of time. The rate of reaction is the concentration of reactants or product divided by the change. The rate at which reaction occurs is influenced by these factors, and we expect you to know these factors. So you can speed up the reaction with temperature. So you can, okay? And, yeah, you can speed it up. It's like, you can speed up the baking of your cake in the oven, but sometimes it doesn't bake quite as well, right? Because you're looking for a certain texture as well. Reaction conditions and add a catalyst. These are the conditions required for rates. So rate is speed, or how fast reaction goes, and it's measured by the activation energy, which is how getting up over the hump, and so it can go to product. Now, we can change this. Adding a catalyst speeds up the rate of reaction by providing an alternative pathway that has a lower activation energy. They only lower the activation energy. The reactor stays the same, the product stays the same, everything's the same except it gets there faster with the catalyst. Everyone follow that?
It's like an enzyme.
That's exactly what an enzyme is, a catalyst. In fact, you're gonna see that. I don't know if it's in this one or later on. In some of these. I think it's in these lectures. Yeah, that's exactly right. It's like an enzyme. That's exactly what it does. Yep. That's why they check their enzymatic levels and all those kinds of things. They want to know how the enzymes are doing. Yep, that's exactly right. An enzyme is a biological catalyst. Very good. So here we have activation energy here, and once you put the enzyme or the catalyst, here it lowers it. So these type pictures we expect you to know. Probably put this picture exactly on there and expect you to label it. Okay? So look for this. Look for this one. If this one is not on this next exam, it will for sure be on the final. Okay, this diagram. Okay? Catalyst in a catalytic converter, and it's required, particularly in the United States, and in most of the countries now around the world. I can't recall which countries. There's some countries that don't require catalytic converters. But catalytic converters are used in automobile engines to reduce pollutants such as carbon monoxide, hydrocarbons including octane, and nitrous oxide. What happens in the catalytic converters, it converts complete combustion is CO2. Incomplete combustion is CO. This catalytic converter not only lowers the activation energy, but actually lowers the activation energy for conversion to complete combustion. You get it? So you don't get your carbon monoxide, which is a poison, right, the silent killer, out your tailpipe. You don't get NOx, which creates smog. Okay? All right? One other, by the way, pollutant, just for you to be aware of, is sulfur. We call them SOx. We have NOx and SOx. NOx is smog, and SOx is acid rain. NOx is also nitric acid rain, but for the most part, we think of acid rain in terms of sulfur compounds. When pollutants pass through the surface, they react with the catalyst and are converted to CO2, which is good, nitrogen, and oxygen and hydrogen. Now, the CO2, because it produces greenhouse gas effects. That's why they talk about driving certain days and don't drive your vehicle when you don't have to. Don't idle your vehicle while you're sitting there listening to your favorite music, okay? Because you're producing greenhouse gases, and there is a greenhouse effect, okay? It is not a conspiracy theory of Al Gore or anybody else, although some of those involved in it have unfortunately presented the scientific information in such a way that it makes absolutely no sense. It does not negate the fact that there is a greenhouse effect. Okay. The reaction reaches chemical equilibrium when no further changes take place in the concentration of the reaction product. So chemical equilibrium means she's balanced now, okay? And your body balances, it works by chemical equilibrium. I can't recall if we've talked about this or not, but I'm pretty sure we'll probably talk about it in the next chapter. But it balances, and pH is a big part of that. So they check the pH of blood and all those kinds of things. How's your pH doing? At equilibrium, the rate of forward reaction is equal to the rate of the reverse reaction. That is an important principle to hold on to. The forward reaction continues. The forward and reverse reactions continue at the same rate. They're just going as fast as it makes it, it goes back. And that's the cool thing about equilibrium. Okay? Base okay for you guys? All right, let's take a look at this. Equilibrium is reached when there is no further change in the concentration of reactants and products. So here you have the reactants. They decrease and they hit this point here and they go along here. Equilibrium of the products goes up like this because you get what? More product. You get it? So you reach more product, less it, and when it hits that concentration where they're both happy being where they are, okay, they're happy in this marriage right here. This is the beautiful part of that marriage. You're early and you're young, you're in the marriage, and just really enjoy this. And at some point you say, get your own bed and we'll just live it out. Okay? It's equilibrium. Okay? You reach that agreement. Okay? All right. This is your grandma and grandpa. Okay, I'm sorry. That's my jokes. But anyway, you get it? It reaches that and it's very happy. It's reached equilibrium. It's good to go. Okay? For the reaction here, A, B plus this, A plus B plus gives you C plus D, and you know these are coefficients, and you know you don't use these coefficients in calculating the molar mass, right? Right. Okay, you only use these for balancing the equation. But now you're going to get to use them in terms of concentrations in an equilibrium. This equation, memorize it. It's always the same, looks the same, never changes. You're going to see it now. You're going to see it in terms of KWs, KC, KEQ, over and over again. Products, concentration of products over reactants raised to the coefficients. Okay? Products over reactants raised to the coefficients. Their own individual coefficient, which means you must have a balanced equation. Okay? Memorize this over and over again. You're going to see this repeated. So, write the equilibrium expression for the following reaction. What's the first step? You see an equation, you must balance the equation. Here we have this equation has been balanced for you. You can check all the numbers to make sure that 6, 6, 2 and 2, we're good to go. Gas, 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 that means where everything's good. So you write the concentration. The bracket means concentration, by the way. And so if you know those values, you simply put those values in. Does everyone follow? So the brackets mean concentration. And I'll either give you the values or I'll find a unique way to have you get them like you did today. You now know how to calculate a molarity. Molarity is moles per liters. So I might say here you had this number of moles and that number of liters. You'll take moles per liter. That's your concentration. The bracket means concentration. So you write the products over reactants always. It's never the other way around. Okay? It's always products over reactants in these equilibrium expressions. And then you raise them to the coefficients. That's it. Do not use the subscripts. Okay? Do not use the subscripts. You only use the coefficients, the values, the small whole numbers in front. And anytime you have molar ratios, they're always small whole numbers in the end. Okay, so everyone see how we did that? I'm going to do another one here. So Kc, numerical values obtained by substituting experimental values of the molar concentrations at equilibrium. So you find the molar concentrations. You see here we have product over reactant raised to the coefficient. And these is H2 and I2 here. A reaction at a specific temperature can only have one value of an equilibrium constant. It's at that temperature, the EQ at that temperature, or Kc, not EQ, the Kc or KEQ at that temperature. The units for Kc depend on a specific equation. In this textbook, Kc is given without units. Keep that in mind. In this textbook, it's given without units, which means when you calc it, you don't have units at the end. Okay? All right? It's textbook, Kc is given without units. Okay? Be aware of that. So, we're going to calculate it. What is the numerical value of Kc at 100 degrees C if a reaction mixture at equilibrium contains 0.4 molar, and you know molar is what? Mole per liter. That's what you see when you see molar, in case you have to use it as a conversion, and 0.13 mole per liter. Okay? And So now we have it in equilibrium. Here we write the expression Kc, products, NO2. And then we have N2O4, reactant is raised to the coefficient because I balanced my equation, the very first thing I do when I see it. Now I simply plug in the values, run the numbers, and you get it, and it's going to be unitless. Notice here, didn't put any of the units in here. We don't put them in. Okay? Heterogeneous equations. Gases, solid, liquid, and states. Earlier someone asked a question about why does this author emphasize this? I said you'll see later in the textbook where it really comes in handy. Some of the early things we were doing did not have the impact. Okay? Now you're starting to see when it comes to pH and equilibrium, whether it's AQ, solid, liquid, gas, you really want to focus in and pay attention to that because that's part of what happens. Why? Watch this. Here we have gas, solid, liquids are part of the reaction. Okay? Solid and liquid concentrations are constant. Solids and liquid concentrations are constant. The K expression is written with only the compounds that are gases. But it's going to be what? Product over what? Reactant. Does everyone follow? Okay? But because it is solid, it's not in the equation. Does everyone follow what happened there? You basically drop it out. As soon as you see solid, ignore it. But make sure it's always product or reactant. In this case, you're good to go, right? Because it just has to be that. Okay? Over 1. But don't write the 1. Please don't. Okay? So everyone see that. The solids drop out. They don't impact it. So we write the balance expression for the following equilibrium. Write the balance equation for HCl and oxygen to give water and chlorine gas. So here we have it. We take a look. We know it's a gas, 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 liquid. We take a look at it and say, okay, what's going to drop out of the equation?
Solids, the liquid.
Liquid in this case, right. Solids and liquids, right. Okay, in this case we have liquids. So they're going to drop out. But we have products over reactants. We raise them to the coefficient. And if we have values, we plug them in. You're going to do this over and over again. So you can write these on your card. Okay, your note card. So you'll have it over and over again. That's what you're going to do. Okay? This we're going to ask you to memorize. The values of Kc can be large or small depending on whether equilibrium is reached. With more products than reactants or the equilibrium is reached, there's more reactants. Reactions with equilibrium constant close to 1 have equal concentration of reaction and products at equilibrium. So this is what we want you to know, right? So here it's a small KEQ, okay? Large AQ, and that's all relative. So greater than 1, less than 1, all for what we will be talking about. Got it? Mostly reactants means it didn't go far enough. Okay? And you can see why, right? This is for products over reactants. Okay? So here we have large one, mostly products greater than the reactants. So you got larger number in the products. Okay? Here you got more what? Reactants. So the value gets smaller. Does everyone follow that? It's just the math. These are basically the math concepts. So we expect you to know that. So you can write this chart or you can grasp the math. So here the effective concentration changes. We have to think about these, and you want you to take a look at this. We will ask you questions like this on the next exam. We will ask you a question, true, false, or multiple choice on this slide. That's slide number 17 in this set. And we will ask you questions like slide number 18 in this particular set. We will ask you these on this next exam. Okay. So find your way of memorizing it. Okay, everybody has their own unique tricks. Increase H, okay, it's going to push out more product. Decrease H, it's not going to push out more product. Get it? So it's going to go back this way. Okay. Increase I2, push out more product. Decrease I2, you're not going to push out more product. So find your own way of thinking about it. Remember it. Decreasing HI. So the more of this you take out, the more of this is going to feed. So you reduce here, it's going to cause this to shift and feed more. It wants to make product. So if you take some away, it's going to say, I have to compensate for that. That's what happens in your body too, and why some people go into shock over certain things. Something's removed, and it's trying to make up that equilibrium. It's making up at a pace that your body just cannot handle. You cannot physiologically handle it, and you fall out or you go into shock. And you lay there for a while, and you relax, you re-equilibrate, okay? And your body's asleep, so it doesn't respond the same way, right? It doesn't fight you. You're not fighting it when you're awake, you're trying to fight. Oh, I need to sit down. No, I can make this next heel. You can't make that next heel, okay? Sit down, okay, you get it? That's what's doing. It's fighting it, okay? And so be aware of that. Oxygen transport. Guess I could have waited. Oxygen transport involves an equilibrium between hemoglobin, oxygen, and oxyhemoglobin. You get it? So you have hemoglobin, oxygen, and oxyhemoglobin. You get it? This is an equilibrium. This is what's happening. When there is high concentration of oxygen, okay, in the lungs, the reaction shifts more to oxygen. So more oxygen, you get more oxyhemoglobin. When oxygen is low in the tissue, the reverse reaction releases oxygen to oxyhemoglobin. Okay? So what do you think happens when grandma or grandpa uses the oxygen tank? We're getting more what? Oxygen and hemoglobin. It's just basic chemistry. That's what's happening. They need it. Okay? And now they have these cute little ones that you don't have to roll around. A great friend of ours in Florida. She called my wife and she said, "Well, I'm on oxygen." I said, "Oh yes, yeah, but don't worry. I looked online. I found this nice little cute one with a nice little cute bag." She likes to stop. She's very stylish. Okay, and she said so she said, "I walk around now with my real stylish oxygen." So it's kind of a cool thing. You need it, you need it. So here at the altitudes of 18,000 feet, a person will obtain 29% less oxygen and may experience. Okay. Get it? Hypozemia is it happens. To a lot of people who do mountain climbing, it's what they do. Guys live for that. And many of them die doing it. It's their life, their choice. Okay? So you're struggling here. And that's what's happening. That's why they carry the bottle of oxygen. Okay? So hypozemia is pretty common when you reach this, but it's a remarkable thing the body is adjusted to for those who live in the heights. Right? They're used to that pressure against them. So here we have it. We write the KC for this. And it's shown here. And you know how to do this now. Product over reactant. Normal atmospheric pressure. Blood goes through. At high altitudes, decreased oxygen, lower pressure. That's why we've been studying PB equals nRT and P1V1 over T1 equals P2 V2 over T2. All these things impact that and impact why and why and how they apply the oxygen and things of that nature, particularly for daredevils. You ever do any mountain climbing? Anybody here did any? You did? Oh yeah?
Yeah, in the Army I was attached to a mountain platoon, so we did a lot of rappelling, climbing, everything like that.
So you can feel it a little bit, or you call it you.
Oh, it's not a joke. It's bad.
Yeah, and that's what's happening. It's really struggling to do equilibrium, and so your body is really trying to do what it should do. Okay, and it struggles to do it, and it's saying, "Wait a minute, I'm not at equilibrium here. Give me a break. And it pushes against the system. And that's just normal chemistry. According to Chatier, this is the guy's principal who did it. By now you probably gathered I don't require you to memorize the famous names. You can if you wish, but it's called the Chatier's principle. It is a principle that we talk a lot about, so this may be one of those names that you hear me say, Le Chatelier's principle. So be aware of this on slide number 22. Shifts the equilibrium direction of the reactants. Okay, depletes the concentration of HbO2, causing hypoxemia. Where am I? So here, remove reactants. Just next part. Oh, okay. I was trying to remember what this came on the next slide. Let's talk about it. Effects of conditions change in equilibrium. So here it is, real summary of it all. This is the PV equals nRT types things. This is why you've been studying those concentrations, C1, V1, etc. And we use the catalyst. So take a look at this. There may be a couple of questions come from this slide. Solubility works similarly. And you'll know it's soluble because it'll say AQ. And if it's soluble, that means it's either a strong electrolyte or a weak electrolyte. And typically, if it's from group 1 and group 2, it's a strong electrolyte. Solubility of salt is quantity that dissolves to form a saturated solution, represented as KSP. So notice here we wrote with products or reactants, but this is the what? Solid. So we don't write the solid. Does everyone see that? Same principle over and over again. Just don't write the solid. And so here you know how to do this, right? What will you do? Look at the concentration of this, concentration of this, and it will tell you that in some form. So write the KSP expression for the slightly soluble salt. So slightly soluble salt, strong, weak, or non-electrolyte. Slightly soluble salt, strong, weak, or non-electrolyte. Sorry? Why'd you say weak?
Because it's slightly.
That's correct. Slightly means it's going to be weak. Okay? So be aware of that. Okay? So you see silver's a slight one because you notice what's, okay, anyway. You see what silver is on the periodic table. It's not even, okay? 1 or 2. Solubility product expression is written here. Why did we write this? Because it is what? Solid. You don't write the solid. The numeric value of the solubility product expression is solubility product constant. Solubility is expressed as the molar solubility, which is the moles of solute dissolved in 1 liter of a saturated solution. So how many moles will go into 1 liter? Sounds like molarity, doesn't it? We can make a saturated solution shown here. Equilibrium mixture contains 5.1 times 10 to the 5 molar. Barium plus 2, carbonate minus 2. You simply look at these values, work it through this problem. This is slide number 27 in this set. We take the concentration of barium. And here, balanced equation. This is the expression. We don't write, right? Barium carbonate, because it's a solid. Therefore, it's this time that gives you this. Some of you are going to take a shortcut and recognize that and say, oh, it's just this time that. You're right. But you better draw this equation for me before you do that. Okay? Your answer is going to be absolutely right. Okay? It's simply these. It's the soluble materials times each other on the product side. Okay, that's it. Okay. These are examples. I don't expect you to memorize these. But this just shows you the difference in them. And when we get to the next chapter, you'll get a better idea of how these exponents work out. Let's take a good break.